You're watching InTechnology, a video cast where you can get smarter about cybersecurity, sustainability, and technology.
Hi, I'm Camille Morehart, host of InTechnology podcast. And today I had a really interesting conversation with Pradeep Dubey. He is Intel Senior Fellow, and he's also a superstar when it comes to parallel computing. Now, the driving workload for parallel computing these days is no surprise, artificial intelligence, or really anything that does massive quantities of digital data processing. So he has, for that reason, quite a lot of perspective on what artificial intelligence is capable of. And we talk a little bit in this conversation about whether artificial intelligence or computers generally are actually ready to transition from what they've been as acting as a system one in helping people with memory and helping people with processing, just computing, so that people can then make decisions and take actions. Are computers and artificial intelligence actually ready now to transition over to system two, where they can actually make perceptual decisions on our behalf and then take actions? Before he came over to Intel, he actually worked at IBM's Watson Lab, and he has worked on parallel computing architecture for the IBM PowerPC, Intel 386, Intel 486 architecture, Intel Pentium, Intel Xeon. He's an IEEE fellow, and he's also recently been named an ACM fellow. Just a really interesting human being and supremely technical. You'll get a little bit of insight into that when he describes some of the mathematics behind parallel computing. Welcome to the podcast, Pradeep. Can you please kick us off by just explaining what is parallel computing and why does it matter?
So parallel computing is the ability to do both parallel instructions and parallel data. Right? Now you can do more and more instructions each cycle on more and more data items each cycle. That's basically what parallel computing is. At a high level, it means doing parallel tasks, doing things in parallel. Now, just to make one fine distinction, sometimes you're simply serving multiple users, right? That's kind of throughput kind of parallelism, right? And each user is not getting served any faster, but you're just serving multiple users. That's one kind of parallel computing. Often that's called some sort of weak scaling. Strong scaling is where you're actually devoting more and more resources, doing things more and more parallel to make one user happier and happier, meaning the latency of that single user, the latency with which the search time is constantly improving. Oh, no, this is painting the picture 10 times faster for me. In one case, the parallelism is being applied to make things 10 times faster for one user. Other case, parallelism being applied to serve 10 times more users.
And you can do them together, right?
We used to think that most things are serial and parallelizing things is hard. That's not true. In fact, most often, most problems can be parallelized. And it's really very few problems which are essentially serial, meaning there's nothing you can do. You just have to wait for one output to start the next process, because the input to the next process depends on the output of the next previous process. There are very few things which are essentially strictly serial. Most things, in fact, have many parallel things that they can do things in parallel. Right now, I'm looking at you. I'm thinking something, what you're going to say next, right? You are doing something while you're talking to me, right? And a whole bunch of things going on in the world parallel, nothing to do with us, right? So things happen in parallel. The world is very highly parallel. That's how billions of people go on living life.
But why design compute that way? I understand you can, but why?
Exactly, because we design compute that way because that's the way to get things done faster, right? And there are things that need to happen very fast. If we don't do that, if we all serialize things unnecessarily, then things will happen slow, right? Good that we'll only need one bus to carry all of us. But we'll all wait for that bus. And that wait may be so long that we all get frustrated because we have one life to live, right?
What are some of the workloads, or what is one of the main computational drivers for parallel computing?
So drivers for parallel computing are like literally any workload that needs a lot of compute. Now, which applications need a lot of compute? That's where, quote unquote, in the old days, there were mainly scientific applications that we knew needed a lot of compute, right? Fluid simulations or some hard optimization problems. These days, the primary source of primary applications that need a lot of compute are the ones that are rooted in dealing with huge amount of data, because data is really what has grown faster than compute could grow. And this massive amount of data has happened because of digitization. Most things are now digital, so they are immediately available to digital world to crunch and make some sense out of it. I mean, if you remember old days, you'll go to dentist, the X-ray was not digital, so it'll take a while before you sit there, right? Nowadays, it's digital, so you see it right there. So pretty much everything, every transaction, every image, every video, every speech, every payroll has become digital. And that has led to immense growth of data. But there's no point growing that data if we cannot do something with it. If we cannot find the photo we are looking for, then might as well go to the old school albums, right? Paper album. But so you must be able to find things that you're looking for. You must be able to mine the data, understand the data, make sense out of data. Otherwise, it just sits there.
And is this where you're essentially leading us toward machine learning or artificial intelligence, which is then used to process or train large quantities of data?
Yes. Machine learning, right? Where somehow you figure out the patterns in data, right? And actionable patterns in data, meaning patterns which we can, once we see that kind of pattern, we know what to do next. That's even better, right? So that's what we can now do much more efficiently. Why? Because we have enough data, enough compute, and smart algorithms that can make sense out of the data. And we are at a point where machines can do a very good job, quote unquote, making sense out of at least a class of data, right? What we call perceptual data. So machines can actually understand images better, videos better, speech better. These are all senses, the way we hear things, we see things, right? Machines can also do that. Almost as good, sometimes even better. But now that you sense the world, what do you do next? Because you have a goal in life. You want to cross the street or you want to make your portfolio go up. Once you sense the data, once you know exactly everyone's chess pieces, you have to make your own move. That thinking, reasoning, decision-making is where machines are now come next. Machines' role will come next logically. Machines are claiming that, no, I can not just crunch numbers. I am not just good at simply perceiving this or sensing the world. Based on that, I can also reason and make a decision for the goal you have in life and take you there faster, make the decision on your behalf. Not only that, just actually make the move, actually act. So sensing, reasoning, and acting is the loop that we humans do all the time. We sense who's where. We decide, okay, based on this, I should cross the road. I should make this turn. And we do that. Everyone does that. Then we sense again. Okay, did I do it right? Oh, man, I misjudged this car. You backtrack, but you keep going. We keep doing that sense, reason, act, sense, reason, act. That loop goes on forever. Machines have not been able to do that loop quite. Now they are increasingly able to do all of that stuff. And the agents now coming up, which are acting on your behalf, are beginning to, right? Leasing agents, hiring agents, all AI. So machines are beginning to do very simple tasks of decision making, not necessarily chess playing, but they're beginning to do that. And that has serious, significant implications.
Given that machines are starting to take over the decision making and the acting, then we have to now provide them with a different type of compute. How do you design systems or architecture with that in mind?
It's beginning to happen, but there's still a lot of hard challenges, right? It's only happening for some tasks. What should you buy next type of stuff. But in many cases, the decision making is not easy. And it's highly complex, especially when you want it done real time. And therefore, we go back to the experts, the human experts for that kind of decision making, right? And think again, most of the stuff, whether it's teaching or singing or dancing, all these things, it's a huge difference between a bad singer, an average singer, and a good singer. Huge difference. Bad teacher, average teacher, and a good teacher. So it's probably easier to beat a bad singer But for machines to actually beat a good singer may be very difficult. So many cases, you can do the typical stuff, right? But that still doesn't mean that you can beat the best, the real expert, the best decision maker, the best, because that's not easy. So point being that you will increasingly begin to do things that we are really good at. And the kind of things we're not good at, machines will take over. That's nothing new. That's always happened. We'll increasingly leave more things to machines. Just like we have left computations to machines, we'll leave some mundane form of decision making to machines, but there's still plenty for us to do. What we have to constantly figure out, how do we get machines to become better and better at such tasks? And someday, maybe even more complex decision makings. Someday, maybe they'll be better than us at anything. We're not there yet.
One of the things you said is that some of the hardest decisions, the most complex decisions for a machine are among the more simple ones for humans. Like a standard mom and pop decision would be maybe extremely hard for a machine, whereas weather prediction really hard for a human, but a machine can pull the model.
It has been the case, but it's changing now, right? Think how humans make tough decisions. Humans don't make tough decisions by actually reasoning through all possibilities. That'd be ideal, but that takes a lot of work. That takes a lot of energy. That's what Daniel Kahneman called system 2, because it requires a lot of energy, a lot of calculations, a lot of energy. The system 2 and human brain probably sucks up more than 25% of energy what you eat. So it's not a cheap task, right? So humans mostly make decisions based on what we call system 1, based on gut feel, which is cheap, right? That's the good part, is that you quickly make a decision, right? You quickly decide that I'm going to buy this stock, right? Bad part is that most of the time you're wrong. If you look at probably nearly all the accidents happen not because of some machine went wrong or a brake failure or anything. It's human decision making was flawed, and not some complex decision making that the traffic conditions were really very complex and somehow this guy just missed something very. No, this was, and why I was looking at why I was texting while turning, I have no idea. That's so dumb. I should have never done that. So we do sometimes very, very dumb things. And most of the accidents are caused by highly avoidable human errors. So humans do make lots of mistakes, sometimes expensive mistakes. Does that mean that they're not capable of taking better decisions? No, most of the time they are capable of making better decisions, but it's not possible to make that decision in real time with the amount of reasoning, amount of thinking it will take. And this is why System 1 developed.
Is there ever a scenario you think where System 1 is better than System 2?
System 1 is better for all such because it's much more real time, much more much faster, much low energy, right? But at the same time, you pay a price for it, right? It can often be wrong, often in hindsight may seem dumb. But that's what we're trying to somehow figure out, that how do we more often than not make a reasoned decision, justifiable decision, right? Thought through decision, informed decision. Who would not want to do that? We all want to do that. But at the same time, I have limitations. I have time limitations, I have energy limitations, I have data limitations, I have information limitation. So under my limitations, help me take the most informed decision. And this is where machines come in naturally, because of course, when a doctor sees you and just asks you 5 questions, what did you eat yesterday? What did you do this? Oh, okay, now here's quite possible that if the doctor was told more of your history, and they tried to look up history, right? But how can they look up your lifetime of your history? But the machines could find some things and think that maybe his sugar has to do with his stress level, which has to do with his recently the meetings he has been having or some life challenge that he's been having. Knowing that doctors, of course, I see now what you should be doing. And absence of that data, the physician is doing the best they can based on what you just told them. Machines can help see some correlations, something in your day-to-day schedule or all the way to your life history or other people's life history who have been like you. Access to that kind of information will make that manager or that physician take much better decision, right? And that's what we are trying to do. That, okay, machines can definitely help because they have so much data access and they can process and crunch so much data real time. We humans have a limited memory. I see hundreds of thousands of patients, so I don't necessarily remember what you told me 3 years back. maybe you have shared with me some things, but I forgot. And you forgot.
Is AI helping to design like parallel computing architecture that will help it improve?
Yeah. So these days we're in this age of AI. So some things are, of course, have a little bit hyped up expectations of AI, but also we have come a long way, right? So any hard problem, the 911 call goes to AI. So one of the hard problem is, how do you design for AI, right? How do we write software easier, better, less buggy, right? More secure, more performant, quicker? Can machine help us? Can machine help me design something hardware, which is still a form of software, better, easier, right? So that I can validate it much sooner, right? So yeah, we're invoking AI, machine learning for such problems that, okay, maybe it can go through my repository of the kind of challenges, bugs, and fixes that I've had. I know my code, but I don't necessarily know how many other people have written bashed this code in past, and maybe the bug that I'm running into, someone else ran into the same bug and fixed it. But there's no documentation. We are all notorious for not documenting things. Often we can't even recognize our own code. That's where machine comes in.
You're talking about that, I would say, more in that like old school sense of using compute power where it has perfect memory and can scan literature for things, CVEs or known vulnerability. But this pivot, like to system 2 that you're talking about, would be using compute differently. It would be trying to grasp.
Yes, so we've always had this idea at a high level that if we could go back and remember everything and just learn from all our mistakes and just look up anything and everything, nothing, we didn't forget anything, we can do better. Yes. Question has always been how? Is there a simpler way, an efficient way to go back and find something similar to what I'm looking for? Find the essence of the data, right? It's not easy because that you have to do what's called in technical lingo high dimensional similarity search, high dimensional indexing, because most problems are very high dimensional, meaning you're not just your looks, your attributes include your parents, your friends, your social network, your history, your kids, your likings, all kinds of stuff. So you have many dimensionalities. Now, which part of your dimensional is really critical to what we are talking now? So what we have become better at is helping machines help us. How do we really go into this high dimensional data and find the attributes that are relevant in my present context? So maybe in the present context, the color of the shoe she's wearing is the best predictor. Okay. But I never knew this. You've probably seen many such things in the news where people saw this correlation. Oh, that people who buy diapers buy beer bottles. Became a very famous one, right? Now, that's a very bizarre correlation, but in hindsight, that makes sense. There's such correlations. We may not know. There is a huge difference between causality and correlation. I may not know who's causing whom, but the two things occur together. Maybe every time I wear a red shirt, it rains. I don't know whether my red shirt is causing the rain or rain is causing me to wear a red shirt, but the two happen together. That correlation is enough in many cases for me to say, okay, man, I'll take an umbrella. Good enough. So people can make their decision without understanding causality, just based on correlation. And correlation is a much easier problem. Machines can simply go in the mounds and mounds of data and say, look, I have no idea, but these two things always happen together. And do seemingly random two things. Someday, with more and more deeper analysis, we'll actually be able to figure out why those two things are correlated and who's causing who. But that may be a long time coming. When we understand that, we'll actually be able to do much more. We'll be able to design some kind of a fix that stop the rain. So machines are now becoming much better. Oftentimes, quickly in a bounds of data, finding these correlations in a very high dimensional space, which way beyond humans can do. And they're doing it, and that's how they're able to make a decision better. Of course, over time, for machines to actually give you better and better predictions, they need to understand that the correlation better and better. Otherwise, they'll not be always right. Because if there is no genuine reason for that correlation, sooner or later you will find data that will start questioning that correlation. No. The point being that you're constantly looking for, yes, most of the time I saw that. I don't know why. Next time with more data, better modeling, I keep beginning to see more insight that is made up of these other three in between things. We call them hidden parameters, right? And you begin to understand things better as you have more and more data or better and better model. That understanding develops over time. Till then, fact that it's actually finding machine is finding such correlations, and therefore many times that's good enough for me to make a decision. And I know it's the same dog curled up very differently. That's fine. That's good enough, right? Why did the dog curl up like this? It never curled up before. No, the reason, but it's my dog. The machine was correct.
Does parallel computing work on CPU as well as GPU?
Yes, that's a system aspect, right? So what it takes to do such a computing is a certain class of problems, a certain class of algorithms need to run fast. At the core of it, it's dense matrix algebra, more importantly, small dense matrix algebra. Call them systolic sometime, right? The matrix multiplication, just like we did SIMD. So that's the kind of stuff that's really needed more often than not. So we're designing machines which can do that better. Similarly, lower precision math, right? Meaning not necessarily I need to capture the range much better. And not like that the numbers have this kind of range is more important. How I represent that average of this range is not that I don't have to be very precise. But if I miss the range, I've lost something much more. So I have to capture the range. But once I capture the range, I don't have to be very precise in what the average of minus 100 and plus million is.
So you're saying if I start with a broad range, I just have to make sure I hit the range. That enables me to do parallel computing?
No, that enables you to do the right kind of arithmetic. So because when you have a finite bits to represent a number in floating point especially, you want to make sure that you divide them up properly. So if I want to make sure that the range is more important, I'll devote more bits to capturing the range and fewer bits to capturing the mantissa, right? We will trade off those bits, that finite bit budget differently. That's what we have done. So that's how AI numerics were created, bfloat 16 and now FP8 and FP4. So with the shared exponents, we keep creating these newer numerics driven by this insight, right? Unaware of this, we were doing them differently. Meaning we're not quite trading off, taking some bits of each. So so the AI is teaching us what kind of things matter more and how we actually deal with a finite budget of our quote unquote bit budget for representing a number, right? And you know that we need to do, that's how we do parallel processing, meaning in a finite width of data, say cache line, we have to back as many data items as we can. How do we back? If each data item takes 64-bit, you can only back fewer of them. So you can only operate on fewer of them each cycle. When that same 64-bit item becomes 4-bit or 8-bit, you can pack 8 times up, right? Or more. But how do you do this 8 times more each cycle? You have to make that 64-bit item become an 8-bit item, or a 16-bit item become a 4-bit item. But you have to do it smartly. Otherwise, you lose the data. And then you're never going to get the right answer, right? You lose accuracy overall. So to maintain the accuracy and still get the benefit of parallel processing, whereby I can operate on more data every cycle, right? You have to make the data items smaller without losing the end result inferencing accuracy at the end. So so it's tied to parallel processing, but it's one element of parallel processing, right? By itself, it doesn't give you parallelism. It gives you parallelism because now you have ability to crunch more data in the same finite budget of your how many bits you can process each cycle.
Anything else that we should worry about anything?
Technically, we need to make everything fast, everything better, cheaper, so that machines can decide better, right? And help us, right? But it's a technology, it's a science, right? You can always use it and misuse it. Looking at this power of computing, there's a concern that will these machines start doing things and making decisions which may be wrong, but then who's responsible if something wrong happens? The machine or the humans behind it? Bar is very high. These kind of ethical considerations, not my expertise, but I clearly know that a lot of stuff we talked about there's a link there. We need to make sure that we do keep doing responsible ethical things so that the technology is constantly used to make us all happier, right? And life better for us.
Do you think it's reasonable? One of the themes that floated around South by Southwest this year was like having in programming AI, having part of that be that AI check itself or have its own, is that realistic in any way?
It's very difficult from what I understand. Right? See, there's always been this challenge of knowledge and being guided by wisdom, right? Can something be self-checking, right? Again, it becomes at some point a philosophical discussion, right? And there's no easy answer that can the question is, what's the goal, right? And what exactly are those things that we universally agreed upon good? That, okay, always make sure that this doesn't happen. What is not supposed to happen ever, right? What's always supposed to happen in all circumstances? There are no easy answers. So without that, what exactly is this self-checking thing? Because you need to set some ultimate good criteria that this is the goodness that you keep maximizing.
Pradeep Dubey, thank you so much for your time, Intel Senior Fellow and superstar in the world of artificial intelligence and the parallel computing architecture that runs it.
Never miss an episode of InTechnology by following us here on YouTube or wherever you get your audio podcasts.
The views and opinions expressed are those of the guests and author and do not necessarily reflect the official policy or position of Intel Corporation.